Very good morning to all of you, all these summer student the participants. The last day, and we are privileged to have Mr. Karandikar with us today. We are celebrating two events together. The first one, of course, this summer program, which will be concluding today, and this 50th year celebration, the Golden Jubilee celebration of science and technology in Kerala. And as a part of that, we have Professor Rajeeva Karandikar is here with us. He is a very, no need of introduction, but there are many young students here. So just to tell you that, he was till recently the director of Chennai Mathematical Institute from 2010 onwards. He is a mathematician, he is a statistician, he is a probabilist, he is a pseudologist. You have to just name that what Professor Rajeeva is not an expert of. And I'm really privileged, as he pointed out, he would have loved to come here, but due to some health restrictions, he hasn't actively started yet the traveling. But I'm sure that Professor Rajeeva will be here. And of course, just to mention you, he is a guiding force for Kerala School of Mathematics. He is our council member, and we always look to him for any kind of guidance. And Professor Rajeeva Karandikar will speak on today, as you see, on connections between the partial differential equations and the diffusion process. Rajeeva.
Thanks for this invitation and the kind introduction. I wish I was there in person, but this is the second best option. All right. So, traditionally, last several decades or maybe even nearly 100 years, there's been a kind of what I consider a artificial decomposition between pure maths and applied maths. And partial differential equations was kind of on both sides, mostly on the applied side, but there is also pure part of it. And diffusion process is part of probability and statistics, which was kept out of this classification most of the time. But over a period of time, slowly it has entered. And that's why in my abstract, I had written that we don't, in the today's talk, to understand, while they will be talk with a lot of probability thrown in, you don't need to have a background in probability theory to still understand what I'm going to say. Okay. So now the starting point is what is called a Wiener measure. Okay. So Wiener measure is a measure defined on the set of all continuous functions from 0 infinity to real numbers. It could also be taken from 0, 1 instead of 0 infinity, if that makes life simpler. But so this was introduced by Wiener about 100 years ago. And after the Lebesgue-Borel the development of what can be now called measure theory, what is being called measure theory. And this, after Lebesgue's introduction, soon I guess they were doing measure theory on Rn. But Wiener's construction, this was the first such example for measure on an infinite dimensional space. Okay, and his things were not existential, but his thing was actually constructive. So he actually defined how would he define this measure in 1920. Okay, so I'm not going, of course, to Wiener's construction, but it can be described in many different ways. So firstly, in the notationally, so we need a measure on W. W is this path space, and notationally, omega denotes a point in capital omega in W, and for every omega you define xi t at W omega to be omega at t. Okay, so it's like coordinate random variables on Rn or coordinate functions on R2 or Rn. Likewise, these are coordinate functions on C. Okay, and this measure is concentrated on functions which are 0 at time 0. So the t is interpreted as time. So because being a probabilist and doing this all the time, I will use phrases which are commonly used in probability. But so at t equal to 0, xi 0 is 0. This set gets the full. So mu, I should have added mu of the whole space is 1. So everything is concentrated on this. And then this is a, you may say, complicated or a simple formula depending on your outlook. But so defining Laplace transform of a set of functions on W, and you have explicit formula given. Okay. Now, probability theory, this plays a very important role, but as I mentioned, this was constructed in 1925, so not 1920, but 1925, and this was years before Kolmogorov proposed this axiomatic framework of probability theory. But okay, here is the alternate description of that measure. So you define or you describe the measure of what can be called one-dimensional sets. Okay, so you fix S and T, you look at xi at T minus xi at S. So, and now this Z will be a function from the set of continuous functions to real numbers now. And if you have a measure mu on W, that is path space, and you take a function, then it will induce a measure on the range space. So mu composed with Z inverse, that is this measure, and that is given by this explicit formula. So this is one-dimensional, and then if you take d-dimensional or m-dimensional things where you take T0, T1, Tm, and then you take this increments in this times, then this mapping, the induced measure, is a product measure. So if you take the differences in the coordinate random variables, and if the intervals are disjoint, then the measure induced on the m-dimensional space, they are independent. So being a product measure in probabilistic language is the same as the corresponding random variables are independent. Okay. I'm trying to describe these things independently also without making a reference to probability, but I will mention what it means probabilistically. Okay. So now people may say, oh, I say no probability, and already I'm bringing in this density function, which is of course central in probability theory. Okay. Now, so this quantity is called the density in the integral, the multiplier here, and this appears is called normal density, or also called Gaussian density. And it's not that some probablist or some statistician introduced the name Gauss to make it acceptable. It was actually introduced by Gauss 200 years ago. Okay. And it's interesting to read history of maths, how it grew, and wherever you have documents available. So there is a beautiful document available here. It's in Classics in Applied Mathematics called by Gauss and Stewart, Theory of Combination of Observational Least Subject to Errors. So whatever the title is actually a translation of the original German writing, which was written in Latin and whatever. But this is a book available, and libraries may have it, and you may try to get it somewhere. This is, I said 200, but here I put written in 1920. No, it is 1820. It's a typo. Okay. So this is just to say that this is not, the word Gaussian density is not something cooked up by somebody, but it is introduced by Gauss himself. Okay. Another interesting thing that recently I discovered, that we all know Weierstrass's theorem, which is then generalized by Stone-Weierstrass theorem. Every continuous function on unit interval is approximable, is uniformly, can be written as uniform limit of polynomials. And this and its variations are used here and there in various techniques in mathematics. I got hold of original writing of Weierstrass, and Weierstrass perhaps doesn't introduce any probability or so on, but this density or this function introduced by Gauss is what appears in Weierstrass's original proof. A convolution of translation of this function f with the original with the function you want to approximate, and gives you a density polynomial, and that he proves converges uniformly. So this bifurcation between pure applied and mathematics statistics, this is all subsequent. Earlier, these were all one continuum, and so Gauss is a mathematician, but he goes and proves this. Or Laplace is a mathematician of highest order. He also has done various things related to this. And Weierstrass has proved, which is a central part or important part of various things in pure math. It starts with this. So anyway, all right. So much for history. All right. Now let's move on. So we come back to the Wiener measure on W. W is the continuous functions, and that I will now call the path space. We think about a continuous function as a path of some motion happening in real world, and if instead of real valued you take three-dimensional, then it would be the motion happening in real world, in our three-dimensional world in which we live. And you can think about RB, and this appeared in Einstein's work on gases and equations of gas and heat equations and so on and so forth, but that later. So on this space W, you think about this coordinate process or coordinate functions that I had introduced, defined by xi t of W to omega be omega t, omega in W. This is called Wiener process or Brownian motion. This is kind of starting point or central to mathematics or probability and theory used. As I mentioned, the same Brownian motion appeared in Einstein's work also. Even before Einstein, it appeared in the thesis in Paris on pure math by mathematics, which has forgotten for ages, but subsequently has become a central part of mathematical finance and option pricing. Okay, but leaving it aside, so we have this measure mu, we have this coordinate functions or process called xi t. Now we introduce a mapping. For a function, you define a new function, p sub t of f, as by this formula. You translate x by this xi t, and now you take integral. Okay. With respect to the measure mu, which is the Wiener measure, you get so this easy to show. This is also a continuous function, and so it's a mapping. So capital T sub t are functions or either operators on C, on the space of continuous functions. Okay, and in order that we are everything is well behaved and we don't get infinities, therefore I have carefully taken functions, bounded continuous functions. C sub b is bounded continuous functions. Okay. Now, this which is written as an integral on an infinite dimensional space. Yeah. Any question? Okay. I think one notational issue. Initially I'd introduced the Wiener measure as functions on R. Essentially, the same thing works with functions on RD, which I did not state, but now I have come to already RD. Okay. So this is a notational thing I did not fix right in the beginning, but or I should have redefined it again, but doesn't matter. Anyway, the capital T sub t is defined explicitly on this page completely. That you define this kernel called Gaussian kernel, and it is given by this formula, and define this integral. Okay. So this P is the fundamental, little p is the fundamental solution to this Cauchy problem. And using properties of the Gaussian kernel and a little bit of simple analysis, one can show that capital T sub t is actually a semi-group, and its generator is half Laplacian. Okay. Now, there's something called probabilistic representation of solution to PDE. We'll be talking more about it later. So it's a simple case which we understand first. So now let's look at the Cauchy problem where you have the little v at capital T it is defined by a function g, and now you're looking at it is backwards. Okay. Then g is a bounded continuous function. So any solution to this can also be represented in terms of the same Gaussian kernel, but we can also represent it in terms of this formula. And the expectation introduced here is basically nothing but integral with respect to d mu, and this xi is an element in the path space. Okay. So I'm slowly bringing closer to the mathematical notation for reasons you will see soon. But right now we can still interpret it as integral of g of x plus zeta, t capital T minus s, d mu s zeta, where mu is the measure on a path space. Okay. Now, one may wonder what good this will do. We already have a nice integral, representing the solution as a convolution of G with respect to this this kernel. Then what is this probabilistic representation giving us? To understand, let me move on to another issue. So let me go to the Dirichlet problem. All of you would have seen versions of this or this somewhere or the other for sure. So given a continuous function on the boundary of the unit sphere, you want to get a continuous function inside on the unit sphere, which agrees with the given function at the boundary. You want it continuous on the entire closed space. Okay. Of course, when you know the problem, you know that it can be solved by explicitly convolving it with what is called the Poisson kernel. All right. Now, here is what is the crux of the so-called probabilistic representation. Okay. So the solution U admits a representation in terms of Brownian motion as before, as follows. Okay. Define a function tau from W to close 0 infinity. We need a closed at infinity, and this tau for a path xi is defined as the first t such that x plus xi of t belongs to the boundary. So SD is the closed unit space and delta is the boundary, the circle, unit circle. Okay. And it will be infinity if it never hits the boundary. This is a continuous function x plus zeta t. It may always be inside, then it is infinity. That's why we have to bring in infinity. And then we define z of xi. So now for every path we define z of xi to be x plus zeta of tau at xi. So at the time it hits boundary, you put that as z of zeta, and otherwise 0 everywhere. And now it can be shown that u of x can be given represented as integral of f of z d mu zeta, where integral is taken on the path space. And probabilistically, we can write it as expected with respect to f of z. Expected is simply weighted average weights coming from the Wiener measure. Okay, notationally, it's easy to see rather than writing it as this infinite dimensional integral. Okay. Once again, the question will be, why go through another one? It doesn't tell you anything more. First, understand what this says by a picture. Okay. So my drawing is not all that great, but anyway. So here is the unit circle, and f is a given function, and we want to define a new function on the closed space. So we want to define for internal point x, we want to define what will our extension be, u of x be. So here is the recipe. You look at any function starting at x. So starting at 0 and replace shifting by x means you are now looking at any function which at 0 is at x. Okay, and you're starting here, and we are now looking at R2 value. D is 2 here, R2 value. Okay, so in the picture it is 2, in the formula it can be any D. So now for any such function, you observe the function till it goes and hits the boundary. And when it hits the boundary, you give the value z of that function is z at the point it hits the boundary. So I have just drawn 3 such functions, okay, and hitting at different points. Their lengths could be different. I have not drawn anything which stays inside at all. It just then the z would be 0. So for every such function, we can assign a value. And clearly, the value there will be functions which start at x, and you take any point on the boundary. There will be functions which will be starting at x, keep wandering inside and hit the boundary at that point. They may return, may not return, but we are looking at the first cut to the boundary, hit to the boundary. Okay, and then we are taking the weighted average over all paths. So clearly, for the circle, it does not give any additional information as representation in terms of Poisson kernel is available. But interestingly, it is valid for episoidal regions. So for me, I didn't have to draw a fresh graph. I just stretched the original function, original graph to this way. Okay. You may say that, okay, you can tweak the Poisson kernel in 2 dimensions to represent a Poisson kernel on ellipse by simple translation. X variable you translate, y you keep same, x you scale. You can get a Poisson kernel for ellipse episoidal. Well, yes, but just wait. Now what? This by no way you can make easy enough transformations and then use standard calculus techniques to get hold of the extended map. So here, the graph is, if it is differentiable curve, smooth curve, maybe. But now I have deliberately chosen a non-smooth curve. So there is a kink at 1, 2, 3, and 4 points. It's not differentiable. Okay? And interesting thing is, the Dirichlet problem on such a space, the same solution works when you are representing probabilistically. Okay, and the proof now starts getting more and more complicated, and there is a condition which is coming in. I'll explain that condition in a minute. But those of you who are interested can read. This is a beautiful source for this is lecture notes of lectures of Varadan at TIFR Bangalore. The lectures were in maybe 1979 or 1980. And there are lecture notes in the standard way that the TIFR lecture notes were available, and you can trace this and get this. Okay. The condition is there in the lecture notes is that I did not. Okay, it is in the previous. All we need is that the region satisfies external cone condition. So that means you take any point on the boundary. Okay, you can have a cone which is completely outside the inside of the space. Okay, so clearly you can see even at this points at which there is a kink, you can take an external cone. Okay, so that cone says that the intersection with the closed closure of your original SD is just the point on SD and nothing inside. Okay, so you can read more about external cone conditions. You want to see mathematical statements and proofs, you can see Varadan's lecture notes. Okay, so this is the first instance of something which can be done as a representation from on the infinite dimensional integral but not at all clear how to do it as just translation of the Poisson kernel in the standard framework. Okay. Somebody can come up with a formula, fine, possible. I'm not ruling it out, but certainly not easy. Now, interesting thing is, now suppose the Dirichlet problem, we tweak it a little. Instead of half Laplacian is 0, you take half Laplacian plus a potential term, hx ux equal to 0. Okay. With Poisson formula, you can write down a translated version of that, and also with the representation formula. We do the same probabilistic representation, but just the expectation here, you multiply f by e power h zeta u. Remember, z is a function on z also. Z is a function of zeta. Zeta is a path in our path space. Okay. So here is the explicit expression. In the Poisson kernel, they will involve some. I have not looked at Poisson kernel writing how it will write, but possible. But this works as soon as your function is your curve is such that external cone condition holds. Okay. Same representation holds. Indeed, let's move on. Instead of just so the Laplacian is a second order term. We added a potential term by multiplying it by h. Now add a first order term. Okay. Gx dot gradient u, and g is RD valued continuously differentiable function. Okay. H a continuous. Now, interesting tweak occurs. You can still do probabilistic representation, way of doing the thing. Earlier, we had just f of z multiplied by this integral h zeta u du. Now we have to add one more term, and more about this term I will tell you on the next slide. So you do an integral of g of zeta s with respect to b of zeta s. Zeta is a function. And immediately somebody should object saying that, but we are taking all continuous function. What if zeta is not differentiable? How will we define this integral? G of zeta s dot b of zeta s. Okay. Zeta is not differentiable. Well, yes. And this also takes us to another theme in probability theory. Again, takes us back 75 years and more. Ito. And this is called the Ito integral in probability theory, and also now called stochastic integral, because Ito introduced it originally when zeta is this Wiener process of Brownian motion, and soon extended going beyond and beyond and beyond. So now it is called stochastic integral, which incidentally has been my area of research starting with my PhD thesis 40 years ago. So as paths of Brownian motion, in fact, all paths of Brownian motion, or almost all paths of Brownian motion, are of unbounded variation. They cannot have differentiability, and therefore integral cannot be treated as a Stiglitz integral. In any case, here we want integral with respect to all paths, and certainly all paths are not differentiable. Okay? And in fact, in Ito's work and subsequent work, it is been known that in fact you want to focus on paths which are for which they are not differentiable, for which you need an extension of this integral. And that's stochastic calculus, and this is integral or stochastic integral. And presentation is valid even when regions are other than unit spheres. Just in the case of unperturbed equation, you will need some conditions on. You don't need smoothness of the region, but you may need things like exterior cone condition, but otherwise valid. Okay. Now, will somebody be interested in such a problem is a different question. All right. So, Brownian motion is a model or is the model for motion of gas molecules in free space in absence of any external force field and when the only motion is due to intramolecular forces. This is going back to Einstein. Macroscopic picture. So if you're not worried about how individual molecules are moving anyway, you can't track them, you can't do anything with them. So you can only do how a collection of molecules is doing. So that is the macroscopic picture. And so the macroscopic picture corresponding to this microscopic picture is exactly the heat equation. Or the number density, the phrase used in physics, the number density is given by this equation that we have already seen earlier and corresponds to our probabilistic representations. And at that time, already there was this talk about what is called a diffusion. And what is that? So let's consider motion of these gas molecules. We at least have some idea about their macroscopic picture, if not individual. Now, in absence of intramolecular interactions, suppose that the motion is given by dxt by dt is bxt dt. So B is some force field. Now, but there is also intramolecular forces. Now what happens? So it was postulated that let's do some additive thing that, there is one part which is coming from this force field and one part coming from intramolecular interactions. And heuristically, that motion from t to t plus delta t, you have bxt delta t coming from the force field, and this is the thing coming from intramolecular forces, where the intramolecular forces may be same, in which case this sigma of xt could be 1 everywhere, or there could be some multiplier. There could be the force field may also be either dampening or expanding the intramolecular forces interactions. Okay, so this and such an object was called a diffusion process. So motion of gas molecules in presence of force field. Okay. And now this is heuristic description, this equation 1. As soon as you see delta t, you know it's a heuristic description. You try to do dt here, what happens? And this was the context in which Ito introduced the stochastic integral. So this one is bxt dt, and integral will make sense, but here you will need integral sigma xt d beta t, and beta is Brownian motion, non-differentiable. So first, these diffusion processes, their macroscopic pictures and how to do computations with respect to macroscopic pictures were developed by a technique called Markov processes. There is an entire body of articles on that theme. So this, you take this only as a macroscopic picture, and you develop some techniques using what are called Markov processes. Ito wanted to give a formal meaning to this microscopic picture, and that is where he introduced stochastic integral. And the Markov thing is something like this. So if you look at the f of xt, you have a process function xt, the motion. You look at f of xt, you take its average. If you start at x and you call that capital T sub t, from equation 1, one could argue that this capital T should again be a semi-group, and we can compute its generator. Okay, so it was argued that this is semi-group and we can compute its generator. And the generator, if you assume very smooth things and you take a smooth the domain, you can show that twice continuously differentiable functions with bounded derivatives is contained in the domain of the generator for this capital T, and the generator is for such functions is given by this formula. It's a second order differential operator. B is the same B which was in our one here, and here this multiplier was sigma, So that gets that's a matrix, and you take the square of that matrix, and that gives you A. And so this is a second order second order differential operator. In writings, there is a bit of confusion. It is often, they don't say that, writings may not say that C2 is part of the domain, and on that subset, the generator is given by this A. Loosely speaking, you say it's a semigroup and its generator is given by this formula. There is a subtle difference that the generator can be bigger depending on which sense you are taking the derivatives of the semigroup, etc. And you have to track that. In any fair way you define the derivatives of the generator, you can show that the C2 is contained in the domain of the generator, and on that the generator agrees with this second order derivative. Okay. But nonetheless, so before Ito introduced this, these things were developed, and then techniques connecting it to PDE and the diffusions were done through Markov business, and lots of things were done. Ito tried to give a formal mathematical representation of that, and thereby he could develop, and he could argue that, well, we can treat these operators where we don't need little b to be smooth. Not initial writings of Ito, but continued. And as long as A is nicely differentiable with B, we can bring down the things required as twice continuous. B to be smooth and continuously differentiable, and A to be, or sigma to be twice continuously differentiable. In fact, Ito had immediately brought it down to sigma to be continuous and Lipschitz, and B to be continuous function. And then his theory worked and derivatives worked. Okay. And that became a big hit. It took a while for Ito's writings to make headway to the rest of the world. Ito did this in the World War II era. It took about 10 years before, or maybe 1951, the first English writings came up, but it was very far fewer people read or understood that. It appeared in a book by Doob 5 years down the road, and then in a lecture notes by Ito at TIFR Mumbai in 1962. So more or less a very authentic English language version of Ito's work is in his own lecture notes at TIFR 1962, referred to in various sources. Okay. Okay, so this is heuristics, and first construction is you start from du by dt as au. This is a formula. Okay, maybe. So I have already come up to this. I did not go over those slides. Okay, Ito defined the stochastic integral in the early 40s to give meaning to. So the earlier one I'm writing in terms of delta. You rewrite this in terms of d, and right now meaningless, but Ito gave meaning to this. And then Ito could give a meaning to this as a differential equation in this stochastic differential equation. And you solve this stochastic differential equation with origin x sub 0 to be at little x, and he called that capital X, little x. That is the solution to this differential equation. And then the semigroup can be given as this expectation, or the average over this. And it is a semigroup which describes the diffusion process, and its extension of its generator is the extension of this differential operator. So this was Ito's construction. Now let me move to third construction, going beyond Ito. Ito's work 1940s, understood in 50s and maybe early 60s. And this is a third construction, and this is due to Strouk and Varadhan in late 60s. As most of you perhaps already know, Varadhan is one of the most known mathematicians today, living today, and of course, certainly amongst the Indian origin. Yes, and he moved to the US after his PhD in India, and this was the early work done after move to US at NYU. He moved there in maybe 63 or so, and soon after that is this work with Strouk. Okay, I'm still trying to describe it, avoiding math as much probabilities as much as possible. But so there is a phrase very popular in probability theory the day to day called martingales. And but what is a martingale? I'll describe it mathematically. Okay, so we already had this thing called capital X. I'm putting a super X to say that Brownian motion, the solution to that differential equation starting at little x. At t equal to 0, it is at little x. So capital X super X is the solution to this differential equation. Then you take a nice smooth function f and you look at f of xt minus 0 to t af. This is the generator, okay, for which you have constructed the solution of the differential equation. So it was observed that this is a martingale. But what does a martingale mean? Okay, you look at this expression in red. So you fix S1, S2, Sk, and little s, Sk is little s, S is less than t. So this is the last S here. And take bounded continuous functions little g1, g2, gk. Then the increment of this m, mft. So mft minus mfs. The increment of mf over this interval t to s, or s to t rather. This is orthogonal in the L2 sense. L2 of the measure mu, underlying on which everything is defined. In the L2 sense to this object, which is product of g's evaluated at x at s1, x at s2, x at sk. So mathematically, mft minus mfs is product is times g of g1 capital X at s1, capital X at sk, etc. This is 0. Our standard orthogonality that you know. Mathematics says independence. So the increment of this is orthogonal to the these are like all observations in the history of the thing which you are looking at. So increments are orthogonal to the history, or in integrals, the increments are independent of the history, and that is what is a martingale. Okay. And what Strouk and Vardhan observed is that requiring that this, you take any function process y as on the path space, okay, and you say that there is some assignment of probabilities on the path space such that these objects mft are martingales, namely this orthogonality holds, okay. Then they observed that integrals of this the products constructed over g of capital X, little x, and y are the same. That means the measures induced on the path space by of y are the same as the measures induced on the path space by capital X. And in probability, we say that capital X, super X, and y have the same distribution. That means induced measures are the same. Okay. So this was a fundamental observation by Strouk and Vardhan. Cornerstone of this is that just requiring them to be martingales is giving you, without any reference to anything else, the full idea of what is the measure induced by y. So, taking a cube, this is my phrase. Vardhan has not told me this, but from the Cauchy problem and heat equation relation, from there they called Strouk and Vardhan called something to be a martingale problem for the operator A. So A is a second order differential operator. So you say that the martingale problem. What is the martingale problem for A? Martingale problem for A is said to be well posed if for every x you can get hold of capital X super X such that apply the generated MF from out of this is a martingale. And if capital A is such that this requirement gives you uniqueness, existence and uniqueness. You can think about this as you can construct a measure on the path space so that the coordinate process satisfies these properties and that such a thing is unique. So just from Cauchy problem, this has been called as Martingale problem by Stroop and Varadhan. And uniqueness, existence and uniqueness of Martingale problem has tons of things which you can derive out of that. Okay, or a conclusion from there. And so you have as this forms a generator, and then that generator, the extension is an extension of the differential operator A that we started. Just the uniqueness of the existence and uniqueness of the Martingale problem gives you that the associated semigroup, and that so there exists a semigroup corresponding to our differential operator that we started with. And Stroop-Varadhan's theory, so as I already mentioned that from classical differential equation techniques to Ito, instead of A being once or twice continuously differentiable, we had come down to this being just Lipschitz and this being any bounded function. And in Stroop-Varadhan techniques, all you need is little a is continuous, but one more little condition, positive definiteness of a matrix, and A to be any bounded. So Stroop and Varadhan showed that if little a is uniformly elliptic, that there exists a delta such that the associated second order derivative, I placed little x here inside aijx. It's always bigger than equal to delta of this. So this is uniformly elliptic. The operators A are the operator A is uniformly elliptic. A depends on x, remember. And also it is continuous with at most quadratic growth, and B is measurable with at most linear growth. Then the Martingale problem for A is well posed. And that's so starting with thinking of a problem from diffusions. What is the diffusion through solutions to differential equations, Ito's extension and Stroop-Varadhan extension? It happened over a 50-year period. And now more than 50 years have elapsed and there has not been added things for that. The Stroop-Varadhan work is still the last word on this. Minor extensions, you can remove this. Instead of this much assumption, you can assume this or that. That's the only thing, but no fundamental addition to that. Okay. And this I have already covered. Now, just like the Dirichlet problem, we had said we can go from A to A plus Q. Now we can move to domains on RD, and we can now start doing Dirichlet problems for A and A plus Q and so on and so forth. Okay, so whole lot of things can be done. There is something called Feynman-Katz formula that you can. I talked about probabilistic representation on the Dirichlet problem on the unit circle. When you look at the similar question on RD, and from that you have this differential equation, you del u by del t au equal to 0 is the standard equation. Now you add a potential to that, and you want to solve this. Well, it admits the representation for the representation is given by this formula, where it's deceptively closer to the formula which I put down in terms of Dirichlet problem on the circle. And this is called Feynman-Katz formula, proven by Mark Katz for Brownian motion, can be extended to other diffusions. And for the Brownian motion, this was using ideas of Feynman. So it is called Feynman-Katz formula, though the formulation and the proof for this is entirely due to Katz, but it fundamentally goes back to ideas of Feynman, and therefore it is called the Feynman-Katz formula. And now you may wonder that what does this probabilistic representation give? Well, if you want to study how the solution works or moves as a, you want to analyze the solution as a function of this little x. So you fix a s and you want to solve, you want to study how does it, is it a continuous function? If so, what is its derivative, if any, and so on and so forth. So you want to study analytical properties of the solution as a function of x. And the probabilistic representation comes in a big way. And not only as a function of x, but you can move in both as a jointly as a function of little s and x. Also, you can do probabilistic solution ideas through the probabilistic solution. Okay, so so you can even in Cauchy problems also you can show that the solutions to the Cauchy problem depend continuously not just on s and x, but continuously on the coefficients a and b. Something much harder to do using analytical tools. So we are looking at solution to this from delta. We should have. So solutions where a and b are there, and we are looking at solutions with respect to operator a. So solution as a function of x analytically is still easier to track, but now we can think of it as how does it change as you change the little a or little b also. Okay, so all these kind of things are available as a technique, the probabilistic representation, and one can go on, but I think it's a good time to stop and move for questions, if any. But you can even tone down from requirement from classical solutions to weak solutions, and then what happens, and then more and more. But let me stop here, and if there are any questions, I can answer those or explain something, and if not, I'll go to the weak solution just for a few minutes. Anyone? It's a too action-packed lecture, so maybe difficult to come up with a quick question, but still, even simplest of questions is welcome.
So there is one question. One of our students, you have to come forward because this mic won't catch.
That what's an equation problem? Dirichlet problem, which we have seen that probabilistic representation can be obtained. I want to know you added some irregularity on the boundary of boundary.
Yes. Yes.
Here we have that probabilistic representation. I want to ask that the representation is unique or not.
Okay. So the representation is unique. So you need some conditions on the whole thing so that the representation is unique. So for example, for the Dirichlet problem, I said that the exterior cone condition in 2 dimension or even in d dimension.
Yeah.
So then the solution is unique and the representation is unique as well. Yes, of course.
And one more, what can we say about the Poisson kernel for if we add some irregularity on the boundary of bounded domain, then whether the Poisson kernel will exist or not, because we have seen in the heat equation that there is some condition on the symmetry of domain, so that we can remove the singularity of fundamental solution of the heat equation. Then here that can be possible or not.
Okay, good question. So you see, it is not to say that only by probabilistic representation you can do all these things and by no other technique. So analytically independent of this probabilistic representation, one can keep developing things by bringing in new ideas in the way differential equations are studied, and a lot of it has been done over a period of time. Some before it came through probabilistic techniques and some maybe after the probabilistic techniques. But the two are complementing each other. So, for example, when we write the representation, From there, you can write it as a convolution with a kernel, and that kernel you can call as the extension of the Poisson kernel.
Yeah.
Okay. So this is a two-way street. Okay. Yeah. Thank you.
Any further question?
Good question. Yes.
Yeah, Rajeeva, maybe if you want to continue, I think no more questions.
Okay. So, so some of you probably, most of you would have heard that there is a whole lot of connection with mathematical finance and option pricing and so on and so forth. And people with study and who have pure mathematicians less, unless their attitude is right, but otherwise people who have worked in applied mathematics and differential equations, and more than them, physicists who are comfortable with these things actually find jobs on Wall Street, and they are applying these things on in mathematical finance. So what is it that these blokes do? What is it that these guys do? Okay, so now, is it valid, not valid? What is its impact on the markets? Is it good, bad? I'm not addressing any of that today. There is itself a whole lot of debates on that. But what they do is, when I came to probabilistic representation, it's still an infinite dimensional object, okay? And you can use it to analyze, you can show it to conclude that some things are continuously varying, some things are differentiably varying with respect to this parameter, that parameter. But in real world, what good it is? So this probabilistic representation have an analog through probability and statistics, where you can actually simulate these objects and compute approximately the average, okay? And that is called simulation techniques, okay? And in mathematical finance, what these people do is apply the simulation techniques and approximately compute the required quantities that are needed for their trading format, okay? And that is what is in vogue a lot, okay? So these things called simulation techniques, in particular Monte Carlo techniques, and in particular called Markov chain Monte Carlo techniques. And especially in this lockdown period, I have become heavy on history. So various things, that lectures that I give, I try to go and read history. And not today, but just a few months ago, I read a whole lot about history of all these Monte Carlo techniques. So unfortunately, their origin goes back to mathematics and physics involved in the Project Manhattan. How many of you have heard what was Project Manhattan, this phrase? Anybody? Okay, at least some raising hands. So Project Manhattan was a secret name given to the mathematicians and physicists working on the atom bomb project in the World War II. The one which was successfully completed and unfortunately was used for Hiroshima and Nagasaki. Okay, so Project Manhattan is the name for that project. And these techniques were developed in that work because you develop lots of mathematical techniques and you have answers in terms of some infinite integrals. What do you do with them? So Monte Carlo techniques and Markov chain Monte Carlo techniques were developed during that period, all classified documents, but for a period of time, some of them found their way in technical writings by people, by Ulam and by Metropolis in 49, and that they called this technique as Monte Carlo techniques. And some of the other techniques used there by Neumann, von Neumann, and it became rejection sampling method of von Neumann. And over a period of time, other than warfare, that is where it is, I'm sure, still being used, then it found a natural thing in finance, and later in what is called Bayesian statistics. But anyway, so it's not just in order to do continuity or differentiability or smoothness of the solutions, but these techniques have been used for some good, for something good or bad. We will leave the verdict for posterity. Let me stop here.
Yeah, so Rajeeva, Professor Tata is here and she wants to say hi to you.
Hello.
Just arrived and she thought that she's there in the last thing, maybe. Check.
Oh, I can't see, so, and I can't even hear.
Yeah, now you can see, I guess.
Yeah.
Yes, she will be giving a talk at 3:30 here.
Okay, good.
This is again the part of that the Golden Jubilee celebration that we have for these students. Maybe.
Is your journey going to bring you to Chennai where we can actually meet?
Yeah, Rajeeva, please say it again.
I want to ask Sujata whether her journey will bring her to Calcutta, to Chennai in this trip sometime soon. So that
CMI. Yeah, what about CMI?
yeah.
Are you going via Chennai? So then
No.
you can.
No, I do want to go to Chennai. I'm here till July or August. I will be in India. So I'm hoping to go because Madhavan and I are discussing some plans.
I know about that plans also.
Know that, right?
So hope you can make a trip here and we can meet. Yes.
But I thought you were not in Chennai. I didn't know you were in Chennai.
Oh no, I was to move to Calcutta and all kinds of things, but my health thing, I had to call that off, and I am continue to be in Chennai and at CMI, and I visit. So if you come here, we will meet. Yes.
I agree, because I also wanted to talk to you about TCG.
Okay. So we'll talk about that separately. I am not moved there, but I am associated with that as well. So remotely. Okay.
Thanks.
Thank you.
Okay, great. So let's give a big hand to.